Vsauce.
Go. So what do you guys want to ask questions about?
The probability.
Okay. Okay, you'll be next in line then. Okay. I don't know. Let's say Matt Stafford has a 60.5% career completion percentage. In some game, he attempts 35 passes. What is the probability he completes exactly 22 of them? So the key to doing this kind of a question is that you know the binomial probability formula. Which is this, where R is the number of successes, N is the number of trials or attempts, Q is the probability of success, and Q is the probability of failure. So in Matt Stafford's situation here, our value for R is?
So P is success?
For Matt Stafford's situation, R is the number of successes is 22 completions, right? The number of trials is 35. The probability of success is got to make it a decimal, so 60.5%. And the probability of failure is 39.5%. Right? Just 100% minus 60.5. And as a decimal. Everybody okay with this? Yes, Riley? 35 minus 22 is 13. Everybody okay with that? So we'll type this into the calculator. So I have 35 math prob NCR 22 times 0.605 to the 22 times times 0.395 to the 13. Enter. And I get about 13.3%. The decimal is fine. Mm-hmm. Yeah, read. Sure. Yeah, let's say at least 34 completions. So what does at least 34 mean? It is greater than or equal to 34, right? So in the case of throwing or completions, that means we could get 34 completions or 35 completions. Why can't I have more than 35? There's only 35 attempts, right? Okay? So that's the same thing as p of x equals 34 plus p of x equals 35. Okay with that? Basically, yes. And now I just apply my formula. Okay with that, Reed? So I just go to my calculator and just kind of type that in. So 35, math, probability, NCR, times 34, times 0.605 to the 34th, times 0.395, plus 35, math, probability, and choose R, 35 times 0.605 to the 35th, and then to the first is just 1, so I'm not going to bother writing it. You could type it in, it's not wrong to do that, but I'm just going to save myself some button pushing. So that is 3.41 times 10 to the negative 7. Or 0.0000341%. Yes, Justina? What if we said at most 33 completions? What does at most mean? Less than or equal to 33. So that would mean x equals 33 or 32 or all the way down to 1 or 0. Oh, you're killing me. I got to type that in 34 times. Isn't there a better way? Yeah. We can do this as a complement. So rather than doing everything under 33, I can take 1 and subtract everything above 33. Notice that this is a strict greater than rather than greater than or equal to. Because here we're including 33, so the stuff above 33 can't include it, right? So that's going to be everything above 33 is 34 or 35. Okay with that? And is it wrong to do it this way? No, it's just really tedious. This way I'm only having to do two probabilities. And in fact, I already have the answer to this. So I can just type that in. No, that's for, that was for x is greater than or equal to 34, which is 34 or 35, right? Which is exactly what we wanted here, right? So I don't have to do anything else. I'm done. because Mr. Kulik was kind and planned ahead to make your life potentially much easier by reusing an answer to a previous problem. Okay, with the probability ones, feel better about that, Reed? Okay. Yes. When am I waiting? Oh, you're just copying? Okay. Riley, I'd asked you to hold on, and I was going to come to you next in questions line. And Claudia, I'll go to you after her. Oh, okay. What's your question? 35 is n minus 22, which is r. So 35 minus 22 is. Happy with that? Okay. Riley, what did you want to talk about? Sure. So let's say I ask you to do this. So to do the binomial theorem, you need to know the formula for the binomial theorem. So this formula, the things that are going to change are these three values. The first one and last one's increased by 1 each step, and that middle one decreases by 1 each step. And we finish when we've iterated from 0 to n. So the spots that are zeros finish when they're now n's. Or the spot that was n is now a 0. So that's how we know when we're finished. So the next one would be n choose 1, a to the n minus 1, b to the first, and we do that a whole bunch of times, and we finish at n choose n, a to the 0, b to the n. Okay with that idea? That's the formula that I'm going to use to do this, but yes, the intermediate step would be just me applying the formula to that. Okay? So this is going to be, in our case, what's my value for n? 5. My value for a is 2x, and my value for b is negative 3. Everybody happy with that? So, yeah, this is the intermediate step that we're doing right now. So that's the first term of my polynomial. What will the next one be? Okay. And then the next one. And 5 choose 3, 2x to the second, negative 3 to the third, and then 5 choose 4, 2x to the first, negative 3 to the fourth, and then 5 choose 5. That's my last one, 2x to the 0, negative 3 to the fifth. So this is the intermediate step. Where we've shown the combinations involved. Everybody happy there? So what our final answer is going to look like, I'm going to have something x to the fifth plus something x to the fourth plus something x to the third plus something x squared plus something x plus something x to the 0 or 1, so I'll just write no x in that spot. Everybody okay so far? Nathan?
Are we ever going to have to do it with two variables like x fourth, y first,
I don't think we saw anything in the homework involving that, so I don't think I put anything. I would found it hard to believe that I would have then suddenly included that on the test. I mean, it just makes it kind of more of a hassle. It would be sneaky. So let's compute the first coefficient. Okay? So I guess before we do that, let's look at the stuff that makes up that first coefficient. So what goes in that blank? Well, 5 choose 0 as a number, and then it multiplies to 2 to the 5th, and it multiplies to negative 3 to the 0. So that's what I'm going to have to compute to go in that first blank. Is everybody okay with that idea? No, your calculator should know the difference. So I'll do 5, math, prob, and choose R, 0, times 2 to the 5th, times parentheses, negative 3 to the 0. So that's 32 for the first one. For the second one, all I need to do is update that last thing that I typed in, correct? I just need to change a couple, 3 numbers. So if I press second and enter, it gives me back what I just typed in. So I'm going to change that 0 to a 1. That 5 to a 4. And that 0 to a 1. And then press enter. So this one is negative 240. And I go continue kind of doing that. Is everybody okay with that? On how I'm getting those coefficients? Riley, does that feel good? Okay. Lily? Sure. I just want to make sure I come up with something that's factorable, so I'll use my calculator to generate something. Yeah, it's not a big deal to generate one. It took all of that long. So I'm just going to decline to finish this one, because all we're doing right now is just typing stuff into the calculator, right? Everybody's okay with that? So let's say we want to factor x cubed minus 2x squared minus 5x plus 6, given that x minus 1 is a factor. So this is a synthetic division problem, really. So this I set equal to 0, and I solve to get x equals 1. That's what number goes on the outside. And then the stuff that goes in here are going to be my coefficients. What do I have to be careful about when I'm putting those coefficients in there? I have to be careful about their sign, but I also have to make sure that I don't skip any terms in my polynomial. So notice here I go from cubed to squared to x to constant. So there's nothing skipped. If I do have a value that's skipped, like if I go from x to the 5th to x to the 3rd, I need to make sure I put a 0 in the place for x to the 4th. So that's something that's easy to forget to do. All right, now I'm ready to start my synthetic division. So the first step is just bringing that first number down. And I do 1 times 1, and I write it under the negative 2. And then I add down, and I do 1 times negative 1. I write it under the negative 5, and I add down, and I do 1 times negative 6, write it under the 6, and add down. For us to proceed, that has to give you 0, because you're told it's a factor. You absolutely should be getting a 0 there. So what this says is, because you got the zero remainder, the divisor is a factor, and the quotient is the other factor. Okay with that, Lily? Okay. Now, hopefully, the piece that's left is something that you can factor some more. So notice that this is a quadratic, so I can factor this by finding two numbers that give me -6 and add to give me -1. Those two numbers are -3 and 2. So if you wanted to go the long way, you could write this as a grouping problem, although that information there, since the leading coefficient is 1, is enough to take you straight to your answer of x minus 3x plus 3, but if you're like, or x minus 3x plus 2, excuse me, if you're like, I don't know, you can do this still too. And since all of those terms are linear now, it's factored completely. Okay with that? Okay. Claudia, I know you were asking about synthetic division when you walked in. Does that feel better? Okay. We can do some more if you still need to, because there's a couple of problems here where you have to use that synthetic division to do. Okay. Sure, yeah. Okay. So how many solutions does x to the 7th plus 3x to the 5th minus 7x plus 8 equal to 0 have? 7. That's it. Okay? So that's like as much as we can really, that's how you use that. It's a really powerful theorem, right? It tells you exactly how many you're going to get, and it's really easy to get. It probably doesn't have a real solution. Like, it probably has solutions that I can't find. Because, yes, in a moment. I was not planning on solving it, so I wrote something that I'm pretty sure is not going to be solvable using our methods. Will you need to solve a polynomial? Yes, but it'll be one that actually is solvable for you. This one, I don't think. So I could ask you to write down the possible rational zeros for something. That's how we use the rational roots theorem. So remember, the possible rational zeros are going to be plus or minus the factors of the constant term divided by the factors of the leading coefficient. So my constant term is 12. The factors of 12 are 1, 2, 3, 4, 6, and 12. My leading coefficient is 2. The factors of 2 are 1 and 2. So my possible rational zeros then are plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, plus or minus 4 over 1, plus or minus 6 over 1, plus or minus 12 over 1. So we've done every constant or factor of 12 over 1. Now we have to do every factor of 12 over 2. So I know technically right now I've duplicated some values on my list, right? Like 6 over 2 is the same as 3 over 1. 4 over 2 is the same as 2. There's a couple like that on there. I don't care if you don't like edit them out. You can just write the list like this, and if you have them written down more than once, that's not a big deal. So that's how you do that. Okay, so I might ask you to just, these are like sub-steps in the solving the polynomial problem, but it's just a way for me to like isolate one particular skill to make sure you can do one particular thing. Bend, bounce, straight.
Why did you pass out the one?
Because I used, that's the first row where I did all of the over 1, and there's the second. So I just was showing you what I was doing. All right, so let's suppose that we have this graph. So here's a graph that you might be given. This is the graph of f of x, and you'd be told, say, f of x has degree 8 or something. So I could ask you, what are the the zeros that we see on this? What zeros do you guys see? Okay. And what kind of 0 is -2? Is that a bend, a bounce, or a straight? That's a bend. Bends look like, where you have like half a parabola on each side. What does bend tell us? It's an odd number greater than or equal to 3. So we could have 3 solutions, 5, 7. Could we do 9? Why not? There's only 8 total, so can't be more than 7. The x equals 3 is a bounce. That means we're going to be doing it in even time. 2, 4, 6. And really, we could write down 8, but we know we can't have 8. Why can't we have 8? Yeah, because, well, this one is already happening at least once, so we have other zeros other than that, so we'll stop there. And 5 is a straight. So that means it's used once, period. But let's look at this a little bit closer, because maybe it doesn't even make sense to have the 7 there, right? So, well, if this is 7, this has to be at least 2, and that's already bigger than 8. So if this one has to be at least 2, and if that one's 7, we have more than 8. Agree? It says once there. What about if this one is 6? Well, this one has to be at least 3. So that's too many, right? Can't be 6. Yep, that's the thing that I'm going to do next. So using this information, I can now make a table of possible solution sets. Yeah, that says once there. So I have 3 solutions that I can see, but I could always have a solution that I can't see. What are those? Imaginary. And then I'll have my total. What's the total always going to be? 8. And x equals 5 is always going to be used, in this case, once, right? Everybody agree with that? So the only ones I have a choice on is the -2 and the +3. So let's write down all the combinations we could have there. So if x minus 2 is used 3 times, x equals 3 could be used 2 times, or x equals 3 could be used 4 times. Everybody agree with that? Or if x minus 2 is used 5 times, x equals 3 could be used 2 times, or it could be used 4 times. Everybody okay with how I did that? Okay, so let's go and look at what we've now written down. So 3 plus 2 is 5, plus 1 more is 6, but I have to get to 8, so what's missing? 2 imaginaries. 3 plus 4 plus 1 is 8, so that leaves room for 0 imaginary. 5 plus 2 plus 1 is 8. That leaves room for 0 imaginary. 5 plus 4 plus 1 is 10. That's impossible, so I'm just going to cross that line out. So what I'm left with is my table of possible solutions. So one of these 3 is going to be how that solution set is broken up. Now up here where we crossed off the 6 and the 7 up here before we even got to the table, if you kept those all the way down to the table and then crossed them off in the table, that's fine. Right? I don't care where you cross them off in that process. Is everybody okay with that? This is like using Venn, bounds, and straights.
What's the difference between like using those and solving the polynomial?
Right, so solving the polynomial is like kind of combining all 3 of those things that we just did into like one problem. But because that's so long and complicated, I tried to give some opportunity to be like, can you do this with just this? Can you do just this part of it? Or just that part of it? Because it's really, you know, like wanting to make sure that I could just single out those skills and add some weight to the test on these most recent topics. So it didn't all come from modules 5 and 6. Or just there was like one monster question from 7, you know. That would be the end of this question. That's all we could, that would be what we'd be asking you to do. Yeah, we can do that. So I'm gonna pick a relatively easy to solve one because we don't have a ton of time left. So I don't want to get it like too overwhelmingly complicated. Is that okay, guys? I mean, we've done more complicated examples than this one. I'd say it's probably a little bit more difficult than this one is. So the fundamental theorem of algebra tells me how many solutions am I going to look for? The rational roots theorem tells me my possible rational zeros are going to be plus or minus 2 and plus or minus 1. Okay. If I go to the graph of this, I'm going to see that x equals 1 is the only thing I see. It's a bounce, so it's going to be used 2 times or 4 times. You guys agree with that? Leading coefficient. So factors of, right? So you have all the factors of 2, so 2 and 1. Yes? Fundamental theorem of algebra?
And do we have to graph it every time we use?
Well, it's the only way you're going to be able to see the bounces or the bends.
Yeah, I like to add one.
So if I draw my little table here, I didn't bother to write the graph down because the bell just buzzed for like 10 minutes remaining and I wanted to get all the way through this problem. So I skipped the typing into my calculator and looking at the picture part. Yes, Riley?
But it's constant over the coefficient.
Factors of the constant over factors of the leading coefficient. So this could be used 2 times, 2 times 4, or 4, 0, 4, right? Those are the only possibilities, right? So let's do the synthetic division now. So x equals 1 is the only one I have to use. So that's good. That tells me that x equals 1 is one of my solutions. And then I take all this other stuff. At this point, you might notice that this looks like you could use grouping on it to solve it. And you certainly could do that here and just exit doing synthetic divisions. But I'll come back and finish it up doing synthetic divisions. But I just wanted to point out to you that this makes the process slightly more expedient if you make that observation. So that's all 4. Now, had you missed that, you'd say, okay, well, let's synthetic division again. The only thing I have to use is 1. It should work again. It did. So that tells me x equals 1 is a solution. And this part tells me what I need to divide next. So maybe I try this one more time. So what that tells me is that x equals 1 was used only once. So there must be some other way to solve this piece. And it's just a quadratic. I can handle that. To solve it, I just subtract the 2 and then square root both sides. And the square root of a negative is I. So there's that. Okay. So again, you can take the synthetic division all the way down until you have like a linear term, but it's usually easier to exit the synthetic division process as quickly as you can when you see something that's either factorable, like I noticed up here, that this piece was factorable, so I exited the synthetic division there. If you didn't notice that, this is quadratic, so you could exit the synthetic division algorithm as soon as you get to a quadratic. And you should not be surprised that you run into like imaginary or irrational solutions where you have to exit the synthetic division algorithm to get to either a factoring part or a quadratic formula part or both. So let's count here. So if I did this route, my 4 solutions are here, 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 and here. Right, multiplicities count. That's part of the fundamental theorem of algebra, right? Or if I went this route, I would have had these 4, and again, it's the same 4 solutions either way of doing it. So that's reassuring. Bryce? Sure. So you have positive I square root 2 is one solution, then you have the negative I square root 2 is a second solution. Yeah. So this is 1 and 2. This is just 1. So I did 2 over 1, and then 1 over 1. I just didn't write the over 1 part. Claudia? I saw that x equals 1 was a solution from looking at the graph. So when I looked at the graph, it looked like this. Yes, Riley? Yes, yeah, if you chose to do it that way. I just subtracted 2 from both sides and square rooted. But you could certainly type in the quadratic formula with 0 as b. That's fine as well. So because there's no x term, I could just solve it directly without using the quadratic formula. But you certainly could use the quadratic formula there also, and that's acceptable. Yeah, do you feel better, guys?